In this video, I'm going to discuss other problems that deal with applications of lines and planes unit, as well as anything else we have learned in the vector units. These are going to be more like tips questions or rich questions that you may see on a test. So first of all, I'm going to discuss a question that was from our textbook from homework, question 14. I think this was day 7. I'm going to do it in 2 different ways. So it says here, the following system of equations represents 3 planes that intersect in a line. And what we don't know about these equations right here, we're told that there's a known p-value here and then this unknown coefficient q. So part A is to find these constants p and q. So method number 1 is most likely what you would go towards. It's just starting to eliminate some variables. So we notice that the coefficients on z, they're all identical, so we can eliminate z. So what I have done is I took equation 2, subtract equation 1 to get this expression right here. And then equation 3, subtract equation 1, gives you this expression here. So I'm going to explain a little bit more in detail about this part right here. So when we have equation 3, so that's 4x, subtract 2x gives us this 2x. Then qy minus y, if you common factor y out, you'll have q minus 1 in front of this y. And then we have this 2 minus the 4, which is this negative 2. Then we want to proceed to eliminate again. So you'll notice how it's probably easiest to eliminate the x now. So I'm going to take this equation on the top, multiply that by 2. So that gives me something that's on the top. And then this equation over here, I just rewrite it underneath. And we know that if we were to add these 2 expressions, the x's will disappear. So once again, when we're adding the coefficients on the y, we have negative 4y's. And then we have this expression of y's. So if we pull out the common factor of y out, we'll have negative 4 plus q minus 1 as a coefficient on the y. And on this side, when we add, we have negative 10 for these like terms collected. Now we know that this question says that these 3 planes intersect in a line, which means it's going to be infinitely many solutions, lots and lots of points on that line. And we know that that happens after result of elimination. Usually we get 0 equals 0. And so what we can say is that the coefficient on the y should be 0, and solve that, gives us the q. And on the other side, this has to be equal to 0 as well, and that gives us the value of p. Okay, so that's one way of doing that. I'm going to proceed to do part B, and then I'll show you a second method for part A that works as well. So in terms of part B, it says determine an equation in parametric form for this line of intersection. So the 2 equations that I found before, let's call them equation 4 and 5. We can plug in the p equals 5 into equation number 4. So equation number 4 is over here. And so the p would be 5 minus 4, which gives you this 1. I guess you could have plugged the q into equation number 5 as well if you wanted to, but it's going to be the same equation or multiple of equation because that's what's happening here for us to get 0 equal to 0. So I used equation 4. You could have done the other. Now we know that a line will always have 1 parameter. A plane has 2 parameters, but a line will have 1. So looking at this last equation that we have here, the easiest variable to create parameter for is the y, because it has a coefficient on it, and x is the easiest one to isolate. So if you were to take that x, move it to this side, and then take the 1, move it to that side, and plug in t as y, you would get this expression for the x. Then we're almost there to have parametric version of this line. We just don't have the z component yet. So let's use equation number 2. Well, you could use any one of these as long as it has z on it. I grab 2 and isolate for z there. So here's the isolation. And now what we want to do is put in what p is. We want to put in what x is, which we found over here. So negative of all of these negatives will make those positive. And instead of the y, we have the t parameter. and collecting like terms gives us this expression for the z component. So a line of intersection, which I call LOI, will be represented by these three components, and you could rewrite them in vector form by saying that these constants create the position vector of a point that we know on the plane, and the coefficients of the parameter is going to be the direction vector of this line. Now, keep in mind that this is not going to be a unique version of this line, because we can have any multiple of the direction vector and really any point that's on the line, and there's infinitely many points on the line. So when you're checking work with a textbook, you have to really pay attention and check your solution with the other solution that's provided. And if you're not sure how to do so, please ask me when you have a chance. So as I promised, let's do question A in method number 2. I like to give you different ways to do it, as I said before, so you have more tools at your fingertips to try different things when you have a harder question. So I've kept the solution that we had before as a verification that we will get the same result. So this particular method, we're going to look at the scenarios of intersections. There were two scenarios that intersected in a line. So it could have been something like that or like that. So with three planes, this doesn't look like it's three planes because maybe two of the planes are actually coincide. So let's look at our normals to see what scenario do we have. So as you know, we can take coefficients of the variables for our normal vectors of the plane. And if you look at the last component here, all of these are 1. But the x component, they're all different here. So none of these could potentially be the multiples of each other. So that means two planes cannot be overlapping at all. So that scenario is out. So we have this scenario. And I've mentioned in notes before that in this particular scenario, the normals will be coplanar. They will fall on the same plane. And there were two ways to check something that three vectors to be coplanar. One of them was doing linear combinations and looking for contradictions. That's pretty long and tedious. I prefer this one. We talked about the triple scalar product. This formula right here is actually very similar to finding a volume of parallelepiped. And if that volume is 0, that means all three vectors that create the box will be all on one plane, because there's no volume to the box equal to 0. So this is really easy to do. I just chose to do the cross product between the two vectors where I don't have unknown value. The order of these really doesn't matter as long as you do the cross product first. So I chose normal 1 and normal 2 because it doesn't have a unknown constant there. So here's me doing the cross product. You may have utilized a different method, that's fine. Just check that you get the same result as me. Here's the cross product. The normal 3 is written over here, and all you have to do is the dot product between them to find that you get the same result for Q. It does not give you P in this method. I guess you can figure out what P would be based on the rest of the question. Okay, another type of TIFS question I can give you is something like this. So this question says, if a point is reflected in a plane, determine the coordinates of its image point. So P prime. So I'm going to actually just call it P1 in my solution, if that's okay. And there's a note that the plane is a right bisector of the line P with its image. So that's what it's showing here. There's a 90-degree angle, and this line segment is the same as length to this line segment on the bottom. So what we're going to do is we're going to locate this point P, let's call it P1. And because we're going to be using vector concepts, we're going to think of it as a position vector from origin to this point 1, P1. But let's go to rewrite it by using a known point P instead. So instead of going from O to P1, we'll go to OP first, and then plus P to P1. Then we're going to define define a point on the plane that is right on the line as well as the plane. Yeah, that's going to be at shortest distance to the point P that's provided. And we've done this type of question before, so we're going to use a kind of similar way to get at this point P1. So first of all, notice that P to P1, so imagine the vector from P all the way down to P1. That means there's going to be actually two of these PR vectors. So P to R, and then if you move it again, P to R, there's two of them to create this P to P1. So that should be making sense. What we want to do next is we don't know what this R is, so we're going to utilize a random point on the plane to help us, like we've done before. So we're going to say the following. In order to find what R is, we're going to say that PR vector, because we don't know what it is here, so we need to find it. The PR vector is going to be a vector projection of PA onto the normal of the plane. So here's my normal of the plane, and these numbers come from the coefficients of the Cartesian equation. We're going to move this normal of the plane to the tail of the vector PA. Then I'd like you to imagine that this normal vector creates a floor on which we're going to project the green vector onto. So at 90 degrees to it, it's going to create this blue highlighted vector right here, which is indeed our vector PR itself. Quick note, if you had AP onto the normal, it's going to be pointing up instead of down. So because we know our goal is to use PR, I just specifically chose to point from P to A so that the direction of this would match what I want. So because A is some random point, we actually need to find it. There's infinitely many points you could choose here. So I chose to plug in 0 for Y and Z and solve for X using this equation that's provided for us for the equation of the plane. That gives me an X value of -33. So point A that I'm going to be using is this point here. Then we need to find PA to project it onto N. So PA is PO plus OA. Why we want to go through the origin is because we want to utilize the actual coordinates of the point because they look identical to components of the position vectors. And so that gives us these components right here for PA. Then we're going to use a vector projection formula, okay, and plug all of these values in. And that will allow us to find the following result. So it actually ends up being pretty nice numbers. We have PR is vector -4, 6, and 8. Now that we have this, we can go back to the original statement here and multiply that by 2 and add it to the original vector position that's pointing at point P. And that will give us this position vector, but you have to rewrite it as the point itself, but the components of the position vector and coordinates of a point will be identical in terms of its notation. Okay, so that solves finding the image point and it utilizes vector projections. Another question I could ask you, and they all could be very different, so please don't memorize anything, just think things through. So here we have, consider a plane containing point A. So point A is on the plane right here. And it has an intersecting line L right here. So this line right here is provided in symmetric form. And this line intersects the plane at point R. So where it intersects into the plane is this R here. Looking at the diagram, you are told, part of the question, that PA is perpendicular. So this is a symbol for perpendicular to the plane. Okay, so PA is perpendicular to the plane. And you're told the point, and you're also told that this particular point happens to be on the line provided as well. Part A, find the Cartesian equation of the plane. So here's the Cartesian equation of the plane, and we know that A, B, C coefficients of these variables should be our normal. We notice that PA, look at the picture, it's at 90 degrees, so PA could be our normal. So because we know P, we're told it right here, we know A up here, so all we have to do is convert the 2 points into position vector or displacement vector PA, using the position vectors pointing at A and pointing at P. So that gives us this result. Then that only gives us A, B, and C. We don't know D yet, so in order to find D, what you want to do is plug in any point that's on the plane. So on the plane, on the picture, we have point R and A, but A is the only one that we know, so I'm going to plug in point A, and that gives us D equals 0, and so Cartesian equation is done. Second part. So what we're going to do is find the intersection point of the line and the plane. And so the line is given to us in this symmetric format, and we have learned that the denominators of this symmetric format would create our direction vector for the line. So the Z technically has over 1, so that's why I have it there. Just be careful when you're pulling these out. You have to take a look at that your variable coefficients don't have anything on them, no negatives, no other numbers, because then you'd have to reorganize it a little bit. And then from the numerators, all the numbers that are supposed to be subtracted from the variables should give us the point or the position vector to the point. So I get 4, -1, and 0 for this line. So if you convert this into vector form, this would be the representation for it. And what we're going to do is find the parametric version of this so that we can plug it into the equation for the plane, which we found in question A. That allows us to solve for the parameter K, and that gives us -7/11 for the parameter K. And once we know the parameter K, we can find the value of the component X, Y, Z using the parametric format. And when we do that, that gives us the point of intersection of the line and the plane, and it is this representation itself. Another question, and this is going to be my last one. Consider the diagram below showing line 1, so here's line 1, intersecting the plane. Excuse me. Line 1 contains the point P, so there's point P on the line, and it has a direction vector M. So on the line we have direction vector M. The plane contains a point A, so here's point A, and also the plane contains vector V. We just don't know one part of this component of vector V. Then you're told a bunch of information. You're given that AP vector is perpendicular to vector B. You're told that a vector projection of AR onto V is this vector right there. And the R, capital R, is a point where the line intersects the plane intersects the line. So we have 3 parts to it. Let's start with part A. We're going to find the value of K. So value of K is on this vector V itself. So we're going to utilize this vector V being perpendicular to vector AP. But we don't have the vector AP yet, so we'll go through the origin to create vector AP using the point A right here that's provided for us and the point P that's provided over here. That gives us vector AP components. Then since AP is perpendicular to V, the dot product between them will be equal to 0. That will allow us to solve for the missing value K, and you get a half. Then part B, we're going to find the point R. So point R right here is on the plane, and we're told this expression over here that vector AR onto V is some vector provided. So we're going to use this to find this point R. Now, because point R is on the line, and we know some things about the line, we know that line is created from position vector with known point P and then some sort of parameter, I'll call it t, with a direction vector m, which is provided in the question. So this is the vector format of the line. Because point R is on this line, we can represent it using these coordinates using the parameter t. We've done this before. Then, because this equation that we're provided here for the vector projection uses AR, we need to find an expression for vector AR. Again, we're going to go through the origin so we can utilize the values that we're told. So we have OR, that's the representation we found using the parameter t, and OA is going to be the same notation as the point A. When you subtract them, you get this expression. So now you have to just plug that in, and vector v with the k value of 1/2 into here. And I'm just going to do it slightly lower because I don't have much space up here. So you can pause and take a look at all my calculations here. This is just a brute force a little bit, doing the simplifications. And at this point right here, what I have done is I've taken this multiple outside of the vector and multiplied it into the vector right here, because we have one vector has to equal to another one. So instead of solving all of the components at the same time, I've highlighted just this y component. We want this y component to be equal to this y component. That creates an equation which we can solve for t, and it gives us t equals 65. Once we know this t, we can find the point R by utilizing what we have here with expressions for t, and we get this result. And on to the last part, which is C, find the plane equation in vector form. So the vector equation of the plane pi is going to be represented by any position of a known point. So we could use OA because we were told point A. We also know point R based on our work prior, so we could put any one of those in here. And then we need to use two parameters. So I have a t and a k. Maybe I shouldn't have used k because k was used before. It doesn't have to be that k. Okay, so forgive me. I'm not going to redo it, but just try to always use different letters, okay? And then we have to use two vectors that are on the plane. So if you look at the picture, we have vector v on the plane and vector AR is on the plane. They cannot be collinear though. Okay, so they cannot be collinear. And if you look at vector AR, where was it? It was over here, and compare it to vector v, you can see that it's not collinear. Just looking at the first component, we have a 0 here, and this component is not going to be 0 if t is 65. So we're okay. And so if you plug everything in, you can see that this is the result. And again, I want to say that this is not unique. So you don't have to use this point A. There's infinitely many points on the plane. You could have used A or R or any number of points. You always want to use something that is easily accessible to you, of course. So this particular vector, because it has a fraction, we can get rid of the fraction and multiply it by a 2. And we will get 081 instead. Also, this vector over here, AR, has a common divisor of 3. So you can divide all of them by 3 to get this result. And the reason why this is doable is because technically this t and k parameters are any real number anyhow, so it really won't matter. So just keep in mind that the solutions that you might be looking at may have a different result. That doesn't mean that you are wrong. And let me know if I can help you to decide whether you're okay or not.